Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Series. And I am very happy to have Elizabeth Melton with us today. Hello, Elizabeth.
Hello.
Well, thank you very much for agreeing to talk about your very lovely article, which we'll get to here in a moment. And Elizabeth, what's your geolocation? Where are you located at?
So I'm actually in Leiden, the Netherlands right now for the Exoplanet 5 conference.
Oh, very cool. Perfect. Couldn't have timed that any better if I wanted to. Very good. Let's see. Summer is in full swing in the Netherlands. And how many hours of darkness? Because we're coming up on solstice. So how many hours of darkness per day roughly are you seeing?
Well, it's getting dark between 10 and 11, just like it is at home.
Yeah. Wow. Very cool. Very cool. Well, hopefully you'll see some northern lights. That would be extra special too. So
that'd be amazing. It's been a little rainy here, but hopefully it'll clear up later.
It's crossed for you. And Elizabeth, what do you like to do for research?
So I have kind of a two-pronged approach. So I really like focusing on the machine learning classifier side of identifying transits in large data sets.
Cool.
But actually, I recently got a job at a primarily undergraduate institution called Rose-Hulman Institute of Technology. It's located in Terre Haute, Indiana. Thank you. And we have access to some small telescopes there. So I've been trying to get students working on ground-based follow-up photometry of exoplanet candidates.
Nice. Beautiful. That's great. Very cool. And that is going to bring us to this very awesome AJ article. Let's blow that up a little bit. It's open access. It's the open access era, people. Go grab a copy for free. DIAmante TESS AutoRegressive Planet Search, DTARPS, 2 hundreds new TESS candidate exoplanets. And Elizabeth, take us away.
So this is the second paper in a series of 3 papers. 2 are currently published. 1 is still in the works, still in review. So the DIAmante or DTARPS project uses DIAmante light curves, which are differential image. Oh my goodness, I just said
analysis.
Analysis. Thank you. Sorry, differential image analysis extracted light curves from the full frame TESS images.
Got it.
So we're still using full frame light curves from TESS. They've just been extracted using a different process.
Okay.
And then what we're applying is the AutoRegressive planet search method. This was first seen by co-author Gabriel Caceres. It was part of his dissertation research. So this is part of my dissertation research at Penn State. I was working under Dr. Eric Feigelson. We're using Dr. Marco Mondalto's DIAmante light curves. Dr. Gabriel Caceres developed the AutoRegressive planet search process, and then Andrew Rosensweet and Colin Abelson were both students who worked on the project and helped contribute significantly to the project.
Good shout out.
So Gabriel Caceres developed the AutoRegressive planet search process. When we're looking for these transiting light curves, we have to extract the noise, and those are usually done through Gaussian processes. But what Gaussian processes generally miss is autoregressive noise. So noise that depends on where you were before in the light curve, and it steps up one little bit at a time.
Right.
So
memory.
What we did is we applied REMA models, which is from econometrics. It stands for Autoregressive Integrated Moving Average.
Yes.
And it's a very old style of getting rid of autoregressive noise in data, but it's still used often, especially for like stock market analysis and stuff like that.
Yep.
So we use that to get rid of the noise for us. And then we made a beautiful random forest classifier, paper 1. Not going to spend too much time on that. And then what we did is after we finished paper 1 and just applying the random forest, we got over 7,000 light curves.
Okay.
So this would be like your transit events that you get out of TESS. And then what paper 2 does is it walks through the vetting process.
Cool.
Where you were trying to be very careful about what we do and analyze it every step of the way.
Okay, nice. Okay.
So if you go to figure 1, then you'll see kind of the overview of our big steps and how we got rid of our things. So we started out with 7,772 candidates from our random forest machine learning classifier.
Okay.
And at the end, we end up with 462 candidates, which we break into level 1 and level 2.
Okay.
If you think of it in terms of used cars, level 1 are ones that you stand behind 100%. Level 2 are still probably pretty good, but you might want to stand off just a little to the side.
Fair enough.
Maybe
Great
not right
analogy.
behind it.
Great analogy. Okay.
And we ended up with 310 what we call galactic plane candidates, which I'll get to those later.
Okay.
So our levels kind of work up from the bottom upwards for our vetting processes.
Okay.
We started out with the centroid test.
Yep.
Very common, the test. We rejected false alarms by eye. We had rejected false positives, some by eye, some through tests, more numerical tests.
Yeah.
We rejected photometric binaries. We applied an ephemeris rejection, and then the rest are level 1 and level 2. So the picture on the left shows the frequency as a term of our random forest prediction number.
Okay.
And the one on the right just shows it in terms of percentage. So you can actually see some of those in there.
I'm with you.
Yep.
Cool.
So the first type of vetting process that we did was this centroid analysis. This was mostly done by our collaborator, Marco Montalto. He used a series of just concentric rings to see where the central light was for each candidate. And if it moved too much, then it was rejected as probably being an eclipsing binary rather than a planet.
Okay.
So that got rid of the majority of our random forest ones. Yeah. If you move down to figure 3, we rejected false alarms by eye. They're not really that interesting. They're just anything that doesn't look like it has any periodicity in it.
Okay.
Figure 3 shows the different types of false positive rejections that we did. So if it's too deep, crazy like that top one, it's likely not a planet. If you have that even odd difference that you see in that second panel, then not a planet. In the third panel down there, what we're looking at is we're looking at a secondary eclipse based on these albedos that are possible. Because when you have close and hot Jupiters, you can't get a small secondary eclipse that you can see. Right. And those are kind of our limits given different albedo parameters. So if it was deeper than that, still no go. And then the fourth one was that we got rid of ones that had the sinusoidal variation that wasn't gotten rid of by our noise reduction processing.
Okay. Good. Okay. So there's our FPs. All right.
So that's the false positives. Going on down, we got rid of the ephemeris matches. So that means the test has these really big pixels. They're 20 arc seconds in length.
Yes.
And so you get multiple stars inside. When you extract the light curve, if you have a really bright star that's doing the variations, then you can get multiple stars that all look like they have the same planet host. Right. And that probably means something wrong is there.
Yep.
Figure 4 here has a couple of weird axes, but it's the ephemeris matching. We followed the same processes used for Kepler from Coughlin et al. 2013. So the little sigmas are basically, it's this natural log difference, inverse ECF, ERF error function. Okay. But you take the difference between the actual periods and you see what their timing is. If the periods look like they happen at the same time, and that's on the y-axis. It's basically this measure of how close are they together. If it's infinity, then it's exactly the same period.
Okay.
It happens at exactly the same time. If it's this square root of 2 factor that they have down here, yeah, if it's way down there at the bottom, then the transits happen at exactly opposite times. On the x-axis, that's how close are the periods actually together. How close are they to being the same period?
Okay.
So the red are everything we rejected. We took all of our candidates, matched them up to everything that was within about 12 test pixels or so, and said, hey, if you have the same period here, or you're working at the same time, you're probably not real. We're going to get rid of you.
Okay.
And that's how we came to our candidates catalog. So if you go down to table 1, it's just a very small sample of our very large
1,000 or 400 or
yep.
So
we have 462 candidates in our DTARPS candidate catalog. We cross-reference these with many other catalogs. This is just a very small sample, but we wanted everything's machine readable table. Sorry.
Yep.
It's all online available. We wanted to make sure we gave everybody all the information that we could for these guys. So we did cross-reference them with the NASA Exoplanet Archive to see their list for planet candidates, confirmed planets, false positives. Great thing about this table is we only have 35 previously identified false positives that actually made it into the final product. So we have what's called a specificity rate, which is statistics for how well do you get rid of the things you want to get rid of.
Okay.
How good are you rejecting your previously identified negatives?
So that's your class.
Yeah, we have over 95% specificity rate.
Cool.
So we get rid of 95% of the previously identified false positives in our catalog. We left the other ones there because that's what we found.
That's what you got. Yeah.
Yep.
Okay.
The full table 1 includes both previously identified candidates, known planets, which we have 81 there, and our new ones, which we have about 191 newly identified candidates in our catalog, which is really cool. And we have information from the star, from our fit, and some of our just parameters from our work through. Sorry.
Good. And there's this very awesome appendix that has all kinds of detail on these things.
Yes. We have a very extensive appendix where we took all of the information we found about it from anybody else's papers that have ever been found on SimPad and stuff like that.
Yeah.
And we threw it into a note that explains a little bit more.
Check it out. Tons of detail on each of these. It's really awesome.
We also have information because we wanted to try and refine our candidate properties a little bit. We actually have information in there as well from DTF. So the Zwicky Transient Facility. This catalog is over year 1 test data, so that's the southern hemisphere. So there weren't a ton of our objects that were in the Zwicky ZTF survey catalog, because that's a northern hemisphere telescope. But what we did look for using ZTF is we looked for blended background eclipsing binaries.
Okay.
So we looked to see if there were any objects nearby that were bright and were also considered variable by ZTF, and how their magnitude changed. We didn't use the Zwicky Transient Facility information to reject any planets. This is part of our refining candidate properties in number 4. We used it to say, you know what, you're a little suspect, or you know what, you look pretty good.
Level 1 or level?
And we level 1 or level 2. It didn't apply to all of them. Again, it's a southern versus northern hemisphere object, but that's what we did. We also used Gaia kinematics to see if, so Gaia is, gives radial velocity measurements for stars.
Yes.
And radial velocity measurements, fine, all stars have them, they're all going through the galaxy. But the problem is if your radial velocity is varying too much, then you probably have an eclipsing binary, not a star.
Right.
Not a planet, sorry. So we use Gaia to to again label some down to level 2s for objects that had too much variability in their radial velocities.
Okay.
But since Gaia does not have time series with radial velocities, we can't use them to actually find any planets specifically.
Right.
Yeah. So if you go down to figure 5, you'll see a couple of our results.
Let's do a zoom out a little bit to get a global, and we'll zoom in as need be.
Yeah. There's 2 different planets there. So if you zoom up on the first planet up top, I can walk you through it a little bit. Okay. So the very top, left, that's the light curve from the DIAmante extracted. And the panel off to the right shows the measure of autocorrelation. So how much does the time steps depend on the previous time steps? Yes. Okay. Yep. And we were able to get rid of that. And then below shows our periodogram from our TCF transit cone filter. The way that our modeling works is we actually change the shape of the light curve. And so we have to use something other than Boxley squares, which is your traditional filter. Right. So we use a TCF filter. Okay. And you can see the planet has a really nice peak right there.
Very cool. And what does the blue cross indicate?
So the blue cross is our peak with the best signal to noise ratio in a little window around the periodogram.
Right. Great.
It's not always the strongest peak that wins generally, but we use signal to noise ratio.
Yes. Yeah. Okay. Cool.
Yeah. And then the one on the bottom is another small, these are both fairly small radii planets candidates. They're all candidates. Very small candidate. The one on the bottom, just below it, is also a fairly shallow candidate. We had, but there's no autoregressive noise that was present in this light curve. Some do, some don't. But even so, our ARIMA methodology was able to get rid of a lot of that noise and was able to pull out that small planet transit.
Very cool. Okay.
Yeah, and these were both previously unknown planets, candidates.
And just for the record, people, there are 462 images in this set. Not in the article, but you can get them.
Yes. Yes.
Very cool.
The author would not have the journal would not have been happy for 462 beautiful snapshots.
Readers would be 462. Very good.
One of the last things we did with these guys, if you want to go down to figure 9. So if you remember back to figure 1, sorry.
Oh, you want to go
if you remember back to figure 1, yeah, you can go ahead.
Sure.
Go up there real quick.
Grab the handle so I get there a little quicker. Figure 4, 3, 2, and 1.
I get all excited. You can see, especially in the right panel right there, that the centroid rejecting dominates across all of those prediction levels. It's just a huge fraction that gets rejected. So down in figure 9, what we did is we took a sample of those that were rejected by centroid analysis.
Okay.
And we wanted to see, yep.
We'll get there, figure 9.
So we took a sample of those that were rejected by centroid analysis. And we said, okay, we're going to pretend like you all passed. And we're going to take a look
where you are
and throw you through everything else.
Okay.
And we found that they were still fairly good candidates.
Hmm.
Just for whatever, we believe that the centroiding was too
Aggressive.
strict. Yeah.
Yeah.
And it mostly rejected planets that were in the galactic plane, or planet candidates in the galactic plane, which it was a crowding measure as well, and it makes sense.
Okay.
So we went ahead and included those guys in as a separate little list. It's kind of an extra bonus list.
Okay. Level 2 star. Okay.
Exactly. Level 3.
Level 3.
These ones didn't pass centroid or
Everything but the center.
right, but everything else looked good.
Yeah.
So we call those galactic plane candidates, and we have those included too as their own little table 4. You get all the same beautiful information, all the same. There were still known planet candidates in there, some false positives, but really the sample itself didn't look any different than our other samples. So there are 310
Okay,
in
good.
the galactic plane list and 462 in our
Yes.
official candidate list.
I'm with you.
And that is pretty much the paper. So this paper is just presenting all of our candidates after taking you through those very careful vetting steps. In our appendix, we have notes on our candidates. That's Appendix A. Those are some of the candidates that we found in the galactic plane. They still look beautiful. We have those, so Appendix A is notes on our DTARPS candidates. It has information if we found it mentioned anywhere else in any other papers, ZTF analysis. We did the same thing for the galactic plane. That's Appendix B. And in Appendix C, we compared it with other surveys.
Good.
Showing that catalog more.
Okay.
For other different types of surveys and analyzing kind of where we rejected and where we stayed on.
Very cool. Very nice. Very nice.
Yeah.
This is one of those gritty papers that I really admire, right? Because you're very detailing on how you did it, what the notes are. Yeah, it's wonderful to have some science in the trench work, as they say here. Elizabeth, I want to thank you so much for walking us through DIAmante paper 2. Very cool.
Thank you.
And you mentioned it a little bit there at the beginning. So you can go ahead and mention a little bit, but I'm curious on, where do we go from here given the published article? So you mentioned that there's paper 3 that's in process. You may want to say a little bit about that one. Is there going to be a paper 4? Is there going to be a paper 5? Can we export this process to other planet hunting missions? Like maybe redo Kepler or go to Euclid or something along those lines. So just kind of, where do we go from here?
So in paper 3, we take a look closer at our candidates. We go through a few different methods to try and get some validation on them.
Okay.
Now, we have a little bit, very small sample of reconnaissance spectroscopy that was followed up with that we just give an outline of. That was done in collaboration with other people. They get to publish the work, but we get to take a peek at our candidates first.
Absolutely.
And we run through a number of other tests. Because we were actually very careful, I mean, exhaustive, but careful, going through paper 1 and paper 2 with our methodology.
Yes.
Paper 3 actually gives very preliminary asterisks, all the caution signs, very preliminary occurrence rates for tests.
Okay.
To compare our methodology with the underlying sample that you would expect from Kepler. So we compare what we get from our catalog with Kepler. We're very good, except we have a lot of objects in the Neptune desert.
Okay.
For paper 3, but we take a much closer look at those objects and go, it might be due a little bit more to the younger stellar age of TESS objects, because it's looking at the whole plane of the sky. So
yeah.
Clusters, whereas Kepler was pointed at one single area away from the galactic plane. So it's a much older population of stars overall. So we float that as a possible reason. We're just finding them. We want other people to go
Interpret them out.
follow them up.
Yes, yes.
So the first three papers were all over year one. It was our first tour with the TESS data. We did 0.9 million stars from year one. It was crazy. It was awesome. We are continuing to do more with that. We're going to do it for all 7 years of TESS. And then we do want to expand. So Gabriel Casarus actually developed the ARPS program for Kepler. So he's already done Kepler. He found 97 new planet candidates for Kepler. But most of them were too faint for follow-up. So that's why we moved to TESS.
Yes.
Got to keep going. But yes, no, we are having some preliminary collaborations out there with other people who are doing big surveys, ground-based surveys, future missions such as the Plateau mission. All of those are great candidates to incorporate aspects of the ARPS survey into it.
Right. Yeah. Cool. Very nice. It will be very exciting to see this develop over the next couple of years. I really look forward to seeing your analysis applied to the multiple years. That'll be very interesting to find out. Cool.
Yeah, can't wait for those longer light curve phases so we can get those smaller planets.
Cross fingers. Cool.
They're there.
All righty. Well, thank you so much, Elizabeth. Appreciate it.
Thank you so much for having me and chatting with me about the paper.
Sure. And that will do, everyone. And I hope this makes your astronomy planet hunting day just a little bit better. And we will see you on the next one. Bye-bye.